Rates of reaction. Now, the rate of chemical change is just the reaction rate. That is the amount of reactant changing per unit time, or how fast the reaction occurs. So if we have these at time 0, we have all these reactants, and then that's the red square. The blue circle are the products, and over time the reaction moves this way. Over time we get more and more product. The time it takes is the reaction rate. How do things react? Well, there's a collision theory that basically says in order for things to react, atoms and molecules must hit each other. They must come in contact with each other. Otherwise they'd never meet and they wouldn't react. So they have to somehow come in contact with each other. If one molecule is 10 miles away from another molecule, they're never going to react. They're not going to meet. They have to be close enough to meet and collide with each other. Now think of molecules as people. In order for them to react or know each other, they have to basically collide with each other. They have to come in contact with each other. In order for some relationship to happen, they have to come in contact with each other. So they need to make sure that they come in contact with each other in order to meet. Otherwise, there won't be any reaction there. So, collision theory, in order to react, molecules and atoms must touch each other. They must hit each other hard enough to react. If you're just walking down the hall and lightly graze someone, they're probably not going to even notice. But if you're walking down the hall and boom, you really hit someone, they are going to react. They might get up in your grill, who knows. You have to hit each other hard enough. And that means they hard enough to break those bonds. Anything that increases how often and how hard will make that reaction faster. So if you can, for example, if you're running down the hall and bash into someone, that's going to make the reaction of that person faster. They're going to react fast. Hey, what's up? If it's a bigger person, like if you put on some football pads, give yourself an extra 30 pounds, bash into someone, that reaction is going to be, hey, what's up? If you're like a fly, you're not going to even really notice anything. If that person will really notice it, the lighter you are. So let's look at this. We have the energy coming here. These are the reactants. This is an awesome little diagram here. And here we go. And finally, there's enough energy to make the products. Now here are the reactants. They're just out here at a certain energy, just chillaxing, enjoying the view. And then somehow they're just given a little bit of energy. It's like, okay, a little more energy, a little more energy. And then all of a sudden they have that energy here that, boom, allows them to go and become products. Notice they split there. So they needed this certain amount of energy applied to them in whatever form to, bam, give them enough of it to finally become a product. Now that energy is the minimum amount of energy they must have in order to react, which is the activation energy. That activation energy right here, boom, that's it. That's the energy that they have to have, those reactants have to have, in order to become an activated complex, energized, then to become a product. So there's always something, they might be relaxing, just chilling out down here. Hey, whatever, these two different products here, two different reactants, they're just right here. Then they're giving enough energy, maybe a push, a shove. If you're walking down the hall, you don't notice anybody, then someone pushes you into another person. That energy activates both of you. It's like when I went to school, or I taught at other schools, there'd be two somewhat enemies, and they would avoid each other in the hallway or in the classroom, but then another person or people would push those two guys together. That push would give them enough energy to meet, and then it was on. They'd start fighting or whatever. So before, they're just kind of separate here. But then given an energy, a push, a shove, they meet, and bam, there's a reaction going. That's the activator. They're activated. They're an activated complex. They had enough activation energy. So activation energy is the minimum energy to make the reaction happen. As they're together, at that point, before they become the product, that's the activated complex or the transition state. So what are the factors that affect reaction rates? Well, temperature, concentration, particle size, and catalyst. So let's see how factors affect reaction rates. And let's use an example at a party. How does temperature have effect on molecules? The same way temperature has an effect on people at parties. If people are at a party and it's freezing out, you're just going to be huddling together. You're not going to be moving around. If there's, let's say, some girlfriends come in here, and then there's some dudes over here. If it's cold, everyone's just going to be huddled together, not mixing around. They are not going to be moving around. But if it's a warm summer night, people are going to be moving around, talking to each other. They're going to be more active. There's more energy. So the more energy is supplied to these molecules, they're going to move around a lot, bump into each other much more often. There's much more energy there. But if it's cold, everyone's just huddled together, not meeting anyone. You know, these guys are just sticking together. These people over here are just sticking together. No interaction. Hot, boom, temperature goes up. Kinetic energy goes up. People are moving around. They're bumping into every other person. Everyone's just having a great time. Everyone's just mixing it up, running into each other. So temperature goes up, the reaction rate's going to go up. People are going to have more chance, or molecules are going to have more chance of hitting other molecules. What about the concentration? Well, let's think about a party. There's just one person there, and there's one person here. You know, and there's one guy here. There's not going to be much of a chance to meet other people. Well, they might meet each other, but that's not going to be much of a reaction. That's not much of a party. But if it's booming with thousands and thousands of people, if everyone's in there, there's thousands of people, thousands of molecules just bashing into each other, there's a reaction that's going to happen. Someone is going to meet someone else. Their molecules are going to collide with each other the more there is. What about particle size? Well, let's just say that there's a big giant in the room, and there's a lot of room there. Catalyst. As a teenager, you probably sleep and sleep and sleep, and you just cannot wake up. Come time to get up to school, you're just sleeping. 7 a.m., you got to get up to school. You're sleeping. You're not waking up. So, parent comes in, let's say your mom, she comes in, get up. You're still sleeping. You're not waking up. She doesn't know what to do. You're just still sleeping. Alarms don't work. Nothing works. Finally, she gets maybe a pitcher full of water, ice cold water, ice cubes, everything, pours it on your head. Still, you don't wake up. You're still sleeping. What the heck? Get up! Now what you need is a catalyst, something to speed up that reaction. Now something like, let's say you're dreaming about a dreamy boy at school. You're thinking about him, who you are absolutely in love with. Since you are in love with him and you want to get to school really fast, you'll wake up and then you will go to school. So a catalyst is increasing the rate of reaction. It will quicken that reaction. You will get up much quicker because of that vision of the dreamboat. So catalyst for the dreamboat, substance that increases the rate of eventually reaction. You would get up by lowering that activation. It would be a long time later, at a party, 10 at night. But the catalyst lowers that activation energy. Quickens catalyst at a party might be a friend that pushes you to go ahead and just meet some person. She might say, hey, go talk to that guy over there. And she'll push you toward him. Otherwise, both of you guys would just stand there. But the catalyst says, hey, go meet that guy. She pushes you over there, and it lowers the energy that you have to get up, the energy that you have to muster up to go talk to him. Catalyst lowers that energy and allows the reaction to occur much quicker. Now, inhibitor, though, will interfere with the action of a catalyst. So the inhibitor, in the same example, let's say this is the catalyst, this is your good friend, and here perhaps you are, and you want to have a reaction or a talk with this one fella. An inhibitor will interfere with the catalyst. So you're over here thinking, oh my gosh, I just want to go talk to him. He's so dreamy. Catalyst pushes you over there and just says, hey, go talk to him. So you go over there and talk to him. But inhibitor will interfere with the catalyst. Doesn't interfere with you, it interferes with the catalyst. Maybe the inhibitor is some other guy. Says, hey, catalyst, I think you're pretty swell. And the catalyst ignores you. She's inhibited by this inhibitor. So she never gets over to push you over to meet this guy. So the inhibitor stops the catalyst. So let's look at the effect of a catalyst on activation energy. Now this is the normal reaction here. This is the activation without a catalyst. It takes a lot of energy to make that happen. But with a catalyst, like, hey, whoop, boom, not as much energy. Beauty of a catalyst. So the thing is, this will take a long time to occur. But with a catalyst, it occurs much quicker. Sometimes the catalyst, the energy will just happen. It takes so long to happen that you don't even notice that it happens. But with a catalyst, boom, it's a much quicker process.